Now this is where the problem comes. Let's say when the signal transmits through the channel, you have you definitely have a lot of noise sources. You have noise imposed on the signal. So how do you remove the noise? So if this is the transmitted signal, this is your transmitted signal. So the received signal would be something like this. Your received signal would look like. Okay, and so on. So this is a 100 you can make out, right, by just by looking at the symbols. So how do you translate this into a perfect signal that was transmitted? The signal that was transmitted was something like this. How do you convert this back into the signal? So the easiest way to do this is repeat the process of quantization. Okay, if you repeat quantization, what quantization does is it cuts off this noise and it keeps the digital symbol representing 1, and then it cuts off this noise, this and this, right? So this is why this is the sole reason why we're using digital communication, because if it was an analog signal and if there was some noise here, then you cannot just quantize this and remove noise, right? Because quantization has voltage levels. This is the input output characteristics of a quantizer. Okay. And this is called the step size of the quantizer. And we're going to look into this when we talk about companding and a lot of other stuff. Adaptive delta modulation. Okay, so let's get back to the signal. Now this signal that was transmitted has been received, and now it has been quantized, and you get the digital representation back. So what do you do with this now? Right? You convert this back into the voltage levels. 1.5, 1.5, and then you use a reconstruction filter to, sort of mirror image the process of sampling. It's the converse of sampling. You reconstruct the signal, and definitely the signal that you obtain now is going to be an approximation of this signal, right? It's going to be a signal that is composed of the values in black. So the new signal that you have that is received is now this. Something like this. Okay, because we had approximated the signal. If it, so greater the number of quantization levels, the more precise is the signal that is received. So the signal is brown is the received signal, if the signal in blue is the transmitted signal. And this whole process, this whole technique of digital communication, you can say, however this is not really in modern day use, is known as PCM. This is your pulse coded modulation, because we coded the signal into voltage pulses, right? And this is a baseband technique. It's used for lower frequencies that are close to zero. Baseband is something like this. This is your, just like your baseband filter, it starts from 0 to some frequency f, right? So so this this is a example of a baseband technique of modulation of digital communication. So if we look at the transmitter and receiver of this system, a PCM system, this is what it looks like. Okay, this is the first communication system that we designed, sort of. This is your sampler, and then you had quantized it, and then we approximated it and then encoded it. So we have an encoder. Sorry for that. This is an encoder. Okay, that's it. And then at the receiver you have change the color now. Again, you quantize it to remove noise. You decode it and you pass it through a filter. And this is your reconstruction filter. Alright, so this is done to remove noise, and then you just mirror image the process. You perform all the converse operations. You decode the encoded signal and you filter out the sampled signal, and you get your data, which was transmitted by the source. This is your destination. So this is your first digital communication system called the PCM, the pulse coded modulation system. And this is probably the easiest possible digital communication system that you're going to study. Now, another thing is that, remember, we left out some space in between the signal representations, and the main constraint when you design communication systems is the bandwidth constraint. Okay, if you use too much bandwidth, you're going to interfere with other stations. And just consider the radio, for example. There are many radio stations coming up, and each of the radio station has taken some frequency and some security bandwidth on either side of the frequency, so that the signal can be transmitted at that particular frequency. And since there's a lot of people communicating and all the bandwidth is being used up, so we are limited to a very small amount of bandwidth for our communication purposes, right? So we need to minimize the bandwidth requirement of the system and still transmit the signal without noise in the perfect replica of the transmitted signal. So when the bandwidth decreases, the signal, just imagine the signal shrinking due to due to low bandwidth, and all these gaps that we left for proper recognition of the signal, they start decreasing. And when the gaps reduce, sometimes this signal could just overlap each other, and the new signal could look something like this. Let's say this was your signal 1 0 0, and then there was some security gap, and then 1 0 0, sorry, 1, and then let's say there was gap, and let's say there was 0 1 0. And now these gaps, when they start reducing, you have something like this, right? So now what do you make out of this signal? You can say this is a 1 0 1 and this is a 0 1 0. Okay, but in fact it was 1 0 0 1 0 0, something like that. Okay, which was the original signal. So this what exactly is happening here? The gap is reducing, so the symbols of the individual binary words, 100 is a binary word, 100 is another binary word, are interfering with each other. Okay, this is a binary symbol and this is a binary symbol of another word. So if they interfere with each other, we get something like this. So since this is like two binary symbols of individual binary words interfering with each other, it is known as intersymbol interference. Okay, so as the bandwidth is decreasing, the intersymbol interference is increasing, the signal is becoming distorted. Okay, so I'm just gonna write this down. As the bandwidth decreases, and we just abbreviate the intersymbol interference as ISI, increases and the signal becomes distorted. So in case of perfect, no constraints of bandwidth and no intersymbol interference, this would be the perfect signal. Okay, and when you observe this signal on the CRO, the oscilloscope, you get something like this. Okay, so if we just zoom into the CRO, it's just going to be two straight lines, right? But when it starts become distorted, let's say it's becoming something like this, you get something apart from the two straight lines. This just shows the distortion on the signal. And let's say it becomes distorted further and you have something like this, then it's going to show a lot of disturbances. And finally, you can see here that the pattern, that this is known as a CRO pattern. You can see here that this is like an eye which closes. This eye closes as you start decreasing the bandwidth and increasing the intersymbol interference. The distortion increases and the eye becomes to close. And this, since this looks like an eye, we call it an eye pattern. All right. So for the ideal eye pattern, there's no bandwidth constraint and there's no intersymbol interference. But as bandwidth starts decreasing and the ISI increases, the eye closes further, right? So this is a closed, almost a completely closed eye, and this is a totally open eye.